Okay, so let's start. Hello everyone, and welcome back to our workshop. So it's a big pleasure for me to present Professor Rosario Paredes. She got her physics degree, her master degree, and her PhD degree here at UNAM. Then she moved to the University of New Mexico in Albuquerque. I cannot pronounce.
In Albuquerque.
And she made a postdoctoral internship there. And now she's back in Mexico. She's a full professor here at the Institute of Physics. And today she's going to talk about relaxation of ferromagnetic domains in a disordered lattice in 2D. Thank you, Rosario.
Of course, Jorge, thank you very much for inviting me and for organizing this workshop. So, this presentation is about a model that we propose to study the relaxation of our ferromagnetic domains in a disordered lattice in 2D. The heart of this work, or the idea, is that starting from a previous work in collaboration with Luis Antonio Gonzalez, who is here, and also with Santiago Caballero, and taking into account an experimental system that was realized 3 years ago, we propose a model based in two things, in the experimental system and that the effects of disorder has in producing localization. So the idea is how ferromagnetic domains move in a disordered lattice in 2D. This work is in collaboration with Cristian Madroñero Carvajal. He's here doing his master in the postgrado en Ciencias Físicas, Gustavo Alexis Domínguez Castro, that is doing his PhD, also in the PCF, and Luis Antonio González García, that is almost finishing his PhD studies. Okay. So this is the outline of the talk. First, I will give some details, just a summary of what is a magnetic domain in the context of condensed matter, and also what is a magnetic domain wall in the same context. And then I will go to our model, that is to our proposal. The idea, as I told you, is that based on an experimental study in which the people studied the many-body localization in 2 dimensions, plus a work done with Luis Antonio González García, that is the heart of his PhD thesis, then we propose this model. This C means the coupled BEC, that the real thing is that we solve coupled Gross-Pitayevsky equations for the condensate, and these Gross-Pitayevsky equations are associated to the ferromagnetic states in the 2D plane, in a 2D plane. After talking about the essential physics that we need to talk about our model, then I will go directly to what we call the quantum protocol for relaxation of a double ferromagnetic initial state. And then, of course, I will give the results based on the numerical simulation or numerical experiments, as you want to call it. And then, with this, I will conclude this part of the main talk, that is the analysis of the motion of the ferromagnetic domains. But at the end, if I think I will have time, I want to talk about just a little bit of a Fermi system in 1D. Why? Because, as you will see, once that we study the physics of localized and extended state within the mean field approximation, that is what we are doing here, there are some remaining questions, but those questions cannot be addressed within the mean field approach. But we have to go further, we have to go beyond, and then there are just very preliminary results of this. So this is a work in progress, indeed, and Alexis Dominguez Castro is doing this work. But just to tell you that these two topics are linked because they are talking about, they deal with the localized and extended states, but in the case of the Fermi system is in the 1D case. Okay, so what about ferromagnetic domains? So what is a magnetic domain? A magnetic domain, within the context of condensed matter, of course, is a spatial region that has a magnetization with a definite orientation and uniform and definite magnetization. So this is a cartoon of what is of a double ferromagnetic domain, and each arrow here represents thousands of elemental constituents, I mean the real atoms, and this is just a cartoon. But this is very similar to what we did in our model. And why? And what is a domain wall? So the domain wall is the interface that separates two or more magnetic domains. Why are so interested these magnetic domains? I mean, for instance, in the context of condensed matter. On one side, we have the practical uses that this stuff has. Among them, we can mention that data storage, sensor, and magnetic motors. But in our case, what we are interested in is in studying the motion of this stuff when they are under the influence of disorder and also are evolve under its own dynamics. In general, the motion of magnetic domains is can be associated to three causes, I think, in general. The causes can be the application of an external field that can be magnetic or electric. Also, we can have a magnetic field plus the presence of a current that is an electric field. And in that case, what we see is that this stuff that is called spin current, polarization spin currents, I'm sorry. But indeed, so we are not interested in the practical uses, of course. So our interest is just to describe the motion of these ferromagnetic domains. And how we will describe this motion? The way in which we will do this description is by considering the intrinsic dynamics in the domains. The intrinsic dynamics is given by two things, by the interactions between the elemental constituents and associated also to the environment or energetic environment in which the ferromagnetic domains are confined. So taking into account these two things, that is the presence of disorder and the interactions present between these two things, we describe the motion or the relaxation of an initial double ferromagnetic domain. This is our work. But first, since disorder is the most important ingredient in our description, let me just summarize the role that the disorder has in giving rise to either localized or extended states. As we know, localization is a phenomenon that can be that is the result of two things, of either interactions between electron and electron or interaction between electron-ion. In the case of electron-electron interaction, the well-known result is the most insulating state. However, in the case of electron-ion interactions, we have several kinds of insulators. They are the band insulators, as Giacomo was telling today, starting with the Drude model, and then the Bloch theorem, and then the tight banding theory. And then we have these band insulators. And also we have the pulse insulators. And these pulse insulators are associated to static deformations of the lattice. And also we have perhaps the most important now, because they are also experimentally accessible in the laboratory, are the Anderson insulator. And the Anderson insulator results from having impurities or imperfection in another perfect lattice. In another case, perfect lattice. So these impurities or imperfections can be of this kind: self-interstitial atom, that is having an atom that normally would not be there, and a substitutional impurity atom, that is an atom of a different kind of mass, or also an interstitial impurity atom, or also a vacancy, that is the absence of an atom. So this Anderson localization, this Anderson insulator is in the which one in which we are interested in to propose our model. In the next transparency, I will give you just a summary of the main results that we use for our model. Perhaps it is important to mention, of course, the seminal work by Anderson, in which named The Absence of Diffusion of Uncertain Random Lattices, in which he described how localization of a single electron is the result of inhibition of transport associated to the destructive interference of wave propagation to different multiple trajectories of the waves. So since Anderson localization is a phenomena associated with waves, then it appears not just in quantum mechanics, but appears in classical physics, as for instance, earthquakes, optics, acoustics, photonics. But here we are interested, of course, in the quantum case. What you see here is that, so this is the first idea, and the important thing is that from that microscopic phenomenon, the macroscopic state of localized and extended state appears. That is the interruption of conduction of electrons. But perhaps the most important thing is that the original Anderson statement is that localization exists no matter with in infinite system, no matter what the dimension of the system is. Whenever we have a certain value of the disordered amplitude. This is the statement of the Anderson localization. But as we know, systems in nature are not infinite, but are finite. Then, since 2008, several laboratories perform experiments showing Anderson localization in 1D and in 3D, sorry. In this case, this is the experiment by Giacomo here, by the group of Giacomo, that is in rubidium-39. And here, this is the experiment done in the Alan Aspect, Alan Aspect people, sorry. And this was done with rubidium-87. And this was done with fermions in 3 dimensions. And this was done in potassium-40, this is potassium-40, and this is rubidium-87. That is fermions and bosons. And what they see here is what Karen was telling today. This is an speckle pattern. And what happened with a condensate, with a cloud, is released through a speckle pattern. So what they observe is that the cloud is localized there are two components. One of the components of the condensate is localized, and the other is expanded. But this is the signature, and this also, and this is also the signature, and also here in these pictures, the signature that the system indeed shows localization. So the conclusion then is that even in the weak interaction case, in the weak disorder case, localized state appears. And how this phenomenon helped us to propose our model. So, and what about, so I told you here about the 3D experiments and 1D experiments, but what about the 2D experiments? And as I told you, 3 years ago, it was proposed, it was performed an experiment to study many-body localization in 2 dimensions. The experiment uses this digital mirror device that Patricia and Giacomo was telling today. No, Giacomo today, Patricia yesterday. I will not explain, of course, the operation of this DMD thing. But the important thing is that they prepare a sample of a cloud of condensate atoms, and then with this DMD device, they produce a disorder, a random pattern, a random line pattern in which the atoms move. So the atoms are initially occupying the whole sphere, the whole plane, like a disk, and then the atoms are released. So this is the quantum quench protocol. The atoms are released, and then the atoms evolve under their own dynamics, under its own dynamics, subject to the influence of disorder and interactions. So the interactions proper of the rubidium-87 atoms. So what they found is that indeed, for a certain value of the disorder in this case is labeled with this delta number, the delta variable. And what they found is that for certain value of delta, the system is localized. And they found this after taking a robust analysis, after doing a robust analysis of the pictures of the snapshots, that is, of the dynamics, indeed, of the particles evolving under the disorder. And then what they found is that when disorder is considered, most of the particles remain in the negative part of this axis. Of this axis. And then this is the signature of a localization phenomenon. But this is the motivation that allows to propose our model. And what else? So the other thing is that the work done by Luis Antonio González Garcia, who is here, and what we did here is to analyze the stationary states of a weakly interacting Bose gas confined in several lattices and with several geometries. The labels here mean an hexagonal lattice, and a square lattice, and a triangular lattice. What we did here is to consider that the lattice is perturbed by this kind of disorder. This epsilon function is a random function defined in the whole grid of our space. And then when we calculate was the stationary states, that is the psi as a function of x and y, as a function of the disorder amplitude. So this is not a cartoon. This is a real thing that the environment of our energy in the case of the bosons confined in the square lattice. What we found? What we found, and what you see here, is that the condensate is as one increase, so here there are several snapshots associated to the stationary states of the condensate for several values of the disorder amplitude. I mean, this is the 80% of the disorder. And Z equal 3, 4, and 5 means hexagonal lattice, that is the coordination tree, square lattice, and triangular lattice. And what we see is that as the disorder is increased, the density of the atoms is isolated in island in the lattice. Instead of occupying the whole lattice, as for instance for a small disorder value, then the condensate occupies small regions. So how we characterize the localization in this case? And remember that in this case we have a weakly interacting gas, that is, there is no strong interactions, but just weak interactions, and then this is why we are solving the Gross-Pitayevsky equation, that is the equation that describes a condensate in its ground state, that is at T equals 0. What we did to characterize these pictures is a large statistical analysis with a lot of snapshots like this. And then these are the observables that we measure. What is H and what is PF? H is the average of the height of the peaks, that is the density of the condensate, and as a function of the disorder amplitude for the different lattices. And PF is the fraction of peaks. Why? Because what we see is that with no disorder, the condensate is distributed in the whole lattice, but when we consider disorder, then the condensate is isolated in island, so like this or like this. This is represented in colors, in density colors. And these were our observables from which we detect that indeed localization occurs, but different. What you can see here is that the dotted line corresponds to the hexagonal lattice. So continuous lines are associated to the same tunneling amplitude, and the dotted line corresponds to a different tunneling amplitude. So the conclusion in this case is that the influence of the geometry has a real influence. So what we see here is that a kind of honeycomb lattice is very robust against the localization phenomena. So it is difficult to observe localization in graphene lattices. This is what we see. What else? We also measure finite size effects. I mean, we perform calculations starting from 500 to 5,000 number of sites, not particles. Remember that we are dealing with a Gross-Pitayevsky equation. So instead of talking about particles, I'm talking about lattice, number of lattice in the site, number of sites in the lattice. Sorry. This finite size analysis, what reflects is that indeed, so what you see here is that several values of the disorder amplitude, and of course for the several lattices, the honeycomb, the square lattice, and the triangular lattice. And what we see here is that indeed, as the system size grows, this fraction peak reaches a maximum, and also in this case we observe the same. So of course we perform numerical simulation until sizes omega such that this number doesn't change anymore. So we measure signatures also of localization by calculating the ground state energy spectrum for this is theta, this is the honeycomb, the square lattice, and the triangular lattice. And the way in which we calculate the energy spectrum is that indeed so what you see here is the energy spectrum in the Fourier space, in the reciprocal space. That is is the result of the contribution associated to the kinetic energy, the potential energy, and the interaction energy. So you see here the three different contributions, and this is just the first relevant zone for each lattice. And what we can see here is that instead of these delta peaks, in the case when we consider disorder, that is this side of the figure, what we observe is that the energy spectrum is continuous instead of just a peaked spectrum. So with this, I think I finished the result from which we inspire to propose our model. Yes, because now, so our model is, so with the results that we got in this study for the stationary state, plus the experimental setup performed 3 years ago, in which the evolution of an initial cloud, half of initial cloud starting in this side, and I mean the negative side of the x then, in the presence of disorders, what we see is that indeed the system is localized. So what is our model? Our model of the ferromagnetic domains is this. So we construct a surface in 2D with that is the result of both an external potential. So this external potential is the sum of two terms. On one side is the harmonic potential, and we include the harmonic potential because indeed in the experiments it is always necessary to take into account this component. And also the potential is composed by the term associated to the square lattice. So we just consider square lattices in our analysis. And as before, we consider that the disorder, that is this coefficient, is given by this function, that is a random function defined across the lattice. And then taking delta varying in the interval minus delta to delta, and delta in the interval 0 and 1. What you see here is the cartoon of two hyperfine spin components of a condensate initially located in these two halves of the plate. What we did is to solve the coupled Gross-Pitayevsky equations for the system. Why? Because in this case we have the parts that I mentioned, the disorder, so that is imprinted here, and the interactions that are here and also here. As Patricia was telling yesterday, in 2 dimensions, the effective interactions must be rescaled for this factor, where LZ means the natural length of the harmonic trap along the Z direction. So these photos are real photos of an experiment of a condensate in 2D. And you can find here easy derivation of how this effective interaction in 2D can be found. I think it's easier than that presented in Slavnikov and Petrov. And what else? So remember that I told you that we are considering the two things, the two aspects, the disorder and the interactions. But in a work published 3 years ago, they studied a mixture of rubidium and sodium atoms, and what they found is that there is a condition that guarantees that these two condensates are not miscible. That is the phase separation. But what we want is not a phase separation. We want the opposite thing. Because since we are interested in studying the dynamics of the magnetic domains, if we impose this condition, that is the the phase separation condition, then we cannot observe the dynamics of the magnetic domains. Instead of that, what we have to ensure is that to select the correct values of these interaction coefficients, effective interaction coefficients, to guarantee that indeed our ferromagnetic states, the motion of ferromagnetic states, can go one over the other, like in the next snapshot I will show you. So what are the observables that we studied? The observables that we studied are, of course, the magnetization in each side. So this is the local magnetization, and it's just the difference between the density of the ferromagnetic, of the density in the left side against the density in the right side, minus the density in the right side. And also we studied the total magnetization on the left side and the absolute magnetization on the right side. What we can see here in this photograph is a snapshot at different times for different values of the disorder amplitude. What we can see here, I think, is that the magnetic domains, when they are evolving in time under, as I told you, their own dynamics and under the presence of this is zero disorder, of course, what they do is just oscillate. But what happens when the magnetic domains are subject to the presence of disorder? And of course, so these snapshots are associated to interactions between, like, this to this value of the interactions. Of course, with this election, we guarantee that indeed we have miscibility of the components. Another thing important to say is that we consider, like in the original experiments, more or less the same number of atoms, the same number of lattice size to do the simulations. And also, the other important thing within the simulation context is that we observe fidelity. Fidelity means that if we evolve the system for a time, I think like this, 3,000 or more, in arbitrary units, then if we change t by minus t, then we get exactly the initial state. So we come back exactly to the initial ferromagnetic state. So this is the form in which we guarantee that our simulations are reliable. We are confident of our simulations, of our results. And this is what we saw. So you can see here that for large values of the disorder amplitude, indeed, the magnetization is preserved. So in yellow represented this component of this hyperfine spin component, and the green one represented the other hyperfine spin component. So this one. I don't know what happened. Has won the figure, you see? So this figure was the snapshot. I don't know what happened. At least you have already seen. Eh? I don't know. Oh. Has won. Well, you saw it.
If you go directly to the
Quizás, Carmen. No, it is not here. Oops. So at least you already saw the image. Sorry. Oops.
Rosario, and in the backward evolution,
Uh-huh.
you use different realization of the stochastic perturbations.
Let me now tell about the number of realizations that we did. So what you see here is that the absolute magnetization on the right side, and in the inset figure you see the magnetization on the left side. What are these shade areas? The shade areas correspond to the root mean deviation of an expensive set of realizations of disorder for a given disorder amplitude. So these are 200 realizations of disorder. What you can see here is that magnetization indeed degrades, I think 60%, is preserved up to 60% of the initial state, right? In the case of the largest value of the disorder amplitude, of course. What happened when we consider another cases of interaction? So these are the results also. This is an expensive set of numerical calculations. Remember that each point in this curve is 200 realization of disorder. And perhaps you can notice that the level at which the final value of the magnetization on the right side changes for different values of the interaction. Interparticle interactions, not inter. I forgot to say, of course, that we consider the same values for the for the particles with the same hyperfine spin state, and also we consider that these interactions are also the same. And as I told you, we consider the inverse of this condition, right? The contrary. So these are the final results of our study. And of course, as I told you, we are not interested in the spintronics or in magnetic storage, but just in studying the dynamics of the ferromagnetic domains initially set. And conclusions for this part are the following. So we propose a model for study the magnetization relaxation as a function of the disordered amplitude. We analyze the magnetization by performing an extensive set of numerical simulation, as I said, 200 simulations for each realization of this, for each disorder amplitude. So what we found is that initial magnetization is preserved as disorder is increased, and here is the value, the largest value of the magnetization that is preserved is 60% of the absolute magnetization. On the right or left side is the same. But what else? So what else regarding this mean field treatment? There are some things to do. Taking into account the long-range dipole-dipole interaction, the real long-range interaction in the magnetic stuff is the project that Christian will develop during his thesis, his master thesis. And also, different geometries and different initial ferromagnetic domains can be set to study the evolution. And what else? What else beyond the extended and localized states? Let me go back just because I want to to say a brief comment about an experiment, actually the experiment done by the group of Giacomo. So what they did is to set an experimental realization of the Aubry-André model. What is the Aubry-André model in one dimension? The Aubry-André model is a quasi-periodic lattice in 1D And what they saw in the experiment is that localization indeed exists, and as disorder is increased. And Anderson localization, it is also called Anderson localization, but disorder is, remember that I mentioned this kind of different static disorders that produce Anderson localization. This figure is not here. Sorry, Alexis. Here was the Hofstadter butterfly.
We saw it.
Wow, cannot be. Okay, what you see here is that in the case of the Aubry-André model, what we find is that there is a critical value or a mobility edge for which the localized state appears. This EPR means the inverse participation ratio. That means the number of particles occupying the lattice in the site as the disorder is increased. And here, this is the inverse participation ratio as a function of disorder. Remember that delta is the label to name the disorder. And what it is found is that there is just a sharp value of this parameter delta for which there exists the extended state, there exists extended or localized states. But where else? What we can do? So nowadays, in the laboratory, people is worried about experiments with ions, but having experiments with ions means having different kind of interactions and not just this nearest neighbor tunneling, like in this case. Then, what happened if instead of this Hamiltonian that has nearest neighbor hopping and the quasi-periodic crystal, remember that a quasi-periodic crystal can be set experimentally as the superposition of two interfering lasers that has two incommensurable wavelengths. Precisely this value beta is the ratio of these wavelengths. And depending on, so strictly speaking, you need to have an incommensurable ratio between these two wavelengths to have this transition. And this is indeed what they saw in the experiment. And, but what happened, or what else, when we are interested not just in extended and localized states? The question is there are any other states that are not localized, not extended? And the answer is yes. These states are called multifractal states. And these multifractal states appear, for instance, when we consider Hamiltonians of this type. So what you see here is that instead of having nearest neighbor hopping, what you have here is a power law hopping. Alpha is a number that can take values from 0 to 0.1, 0.2, 1, 3, like the dipolar interaction. You can have also the interactions, can be contact interactions like this one, but if you have Rydberg atoms, then you have to include not just contact interactions, but interactions depending on the distance. I mean, Coulomb interactions. What happened when we have this kind of Hamiltonian? So what Alexis is doing is to consider change of, so I will show you just the results with one excitation. Excitation means one spin up and the other spins in the change are down. The simulations that Alexis is doing have around 1,000 sites, sorry. he uses open boundary conditions, and what they do is to perform an exact diagonalization and then to obtain the evolution of a given initial state. A given initial state means to have an excitation at the center of the chain, and then to see how this excitation evolves under the influence of this kind of hopping law, and also associated to the contact interactions, and also associated to the fact that there is a quasi-periodic lattice. What Alexis has found up to now is that these are the results for a single particle. What you can see here is that these are different values for the power law exponent, this alpha, the hopping power law. And what you see here is the propagation of this excitation as a function of time. And what we can see here is a ballistic expansion in the case of the dipolar dipolar hopping, sorry. But when we have a Coulomb hopping, instead of this ballistic expansion, the things changes, and of course this evolution. But what happened when the power law exponent takes the value 0.5, and these plots correspond to delta, to disorder amplitude equal to 0, and this corresponds to disorder amplitude of 8. We cannot see here, but in the real pictures, what one can see here is that a kind of interference associated to the fact that the particles see the whole particle I and particle situated inside I and particle situated inside J can see at every side, at every position in the lattice, and then it is not seen here, I'm sorry, but in the real figure, one can observe a kind of interference here associated to the long range of this hopping law power hopping law, sorry. And what happened when we add disorder? So this is the case with no disorder, and this is the case with disorder. What you can see here, instead, again, here you should see this interference phenomena, but you are just seeing localized, that there is no propagation, and that the particle still remains localized at the 0 position, labeled here. And what else? So Alexis studied this function called the survival function, and is determined by, once that the evolution of the initial state is known, as I told you, by an exact diagonalization of the system, then it is possible to determine the survival function, this f of I and t dependent function. And this function is just what is the survival probability in between the sides minus I/2 and I/2. So this is a kind of phase diagram of this quantity, the survival function. And why I wanted to show you this diagram, because although it is not here, and it's one of the transparencies that I lost, there is a quite similar phase diagram found by another methods. Just related with the exact diagonalization, and it is exactly the same, and it has exactly the same form. And, but what else? So there is work in progress. This is why you see here an interrogation, because the work in progress is what is the phase diagram associated to the influence of interactions and disorder. So this is work in progress. This is not done already. And with this, I think I will go to the conclusions. And remember that for the study of the ferromagnetic domains, we propose a model for study the realization of magnetization as a function of the disorder amplitude by analyzing several observables, in particular the magnetization, the local and absolute magnetization on left and right sides. We observe that as the disorder has its maximum value, then magnetization is preserved up to 60%. We perform, as I told you, an expensive set of numerical calculations. And what else? The work that Christian will do is to consider long-range dipole-dipole interaction that are indeed the important interactions in the case of magnetic stuff. And I present just a brief summary of the result obtained up to now of the Alexis work regarding the Fermi system, in which we study the full quantum dynamics with the interest of addressing the question, what is in between between the localized and extended states. As I told you, there is a recent work, it's not here, the citation, a recent work published this year, in which they found that indeed there exist these fractal states. And our purpose is taking into account this Hamiltonian. So in the work recently published, they just consider these two terms with no interactions. And our goal is to consider also the interactions and to get this phase diagram to see if there is another kind of phases, not just the multifractal phases or multifractal states, but other things. And that's it. And thank you very much.
Thank you, Rosario, for this very interesting talk. And we have time for a couple of questions. Victor.
Rosario, thank you very much for the talk. I was wondering, when you mentioned this interference of two lasers of slightly different wavelength, did you set that right?
Here, Karen? No. Beta.
Beta.
Ah,
Beta.
beta. Beta is the ratio. In this experiment, the lattice, the quasi-periodic lattice, was formed as a result of two interfering lasers having two different wavelengths, such that the ratio of one of them is incommensurable with respect to the other.
Yeah.
And this is a quasi-periodic lattice.
Yeah, I was puzzled by that result, because isn't it that they are mutually incoherent, the lasers, or perhaps
No.
I don't know what exactly, how to achieve this interference of slightly, or perhaps beatings, or
No,
I'm
perhaps Giacomo has the answer.
Uh-huh. Oh, okay, it's beatings. Yeah, thank you.
Because it's not incommensurate at the level of it's enough incommensurate for the effect. It's not the
What I said is that, strictly speaking, you need to have a real incommensurate wavelengths, I mean the value of beta, if you want to see localized states. Well, as Giacomo said, in the case of these almost incommensurable wavelengths, what you observe is that localization in one dimension for this quasi-periodic lattice.
Okay, thank you.
You said you solved the full quantum. How many? So there were 1,000 sites.
Yes,
What
1,000
is-
sites.
And what is the size of the matrix?
Alexis, what is the size of the matrix?
Just curious.
Oh yes. I forgot to tell you. In the case, thank you very much for the question. In the case of this Hamiltonian, these results correspond to a 1,000 change, but with no interactions, with this term equal to 0. When interactions are considered, the largest size of the change is about 150, Alexis, about, near? With this full quantum.
Those are spinless fermions, right? So those that you have are spinless fermions, right? So you don't have any. So it's just different side, but there is no spin, right? Or what?
So
I mean, in the Hamiltonian, there
each-
you wrote. I mean, in the Hamiltonian, there's no spin index, right?
No.
So
It's-
those
we
are
are talking
spinless,
about
right?
those excitations,
Okay.
okay?
So it's just one particle, I guess, and then 1,000 sites. Okay.
Of course,
Okay.
Santiago. Thank you very much.
Okay.
This is just one particle, and the work in progress is considering two excitations. Okay?
But the point is that it is full quantum.
It's full quantum. This is the point, the important point. Yes.
More questions? So I have two questions.
Yes.
So in this last part, why is where the fractality comes from? Where is the self-similarity in this problem?
Let me show you, if I can, this, what I'm talking about. Alexis, do you remember the reference of the, no, you don't remember, right? Because I cannot find now this reference, but I think it's here. The Firreblet, Jorge, just give me a minute. If not, I can show you later.
No problem.
You now know all the things I have. Sorry. No, these are Victor stuffs. No. Sorry. No, I cannot find it. Sorry, Jorge. But what?
Okay.
These multifractal states are the signature of this multifractal state is found when you consider the difference between the levels, between the energy levels of this Hamiltonian, and what you see here is that the energy levels are associated like in a fractal. They exhibit something like filamentary behavior, which is what precisely characterizes the self-similarity case, and also this self-similarity that I was telling.
So this is why you were showing, so the energy spectrum is a Hofstadter butterfly or something.
Yes, exactly.
But it disappeared.
Yes, I don't know why.
Okay.
Yeah. not just that. So the work is the work that I mentioned that was recently published this year, I think this month, by Slavnikov. And in that work, what they do is that calculate the difference in energy levels, and they found this self-similarity or filamentary energy spectrum associated to self-similarity states that I told. Yeah. And we hope, we expect to find the same characteristic with this system.
Okay, thank you.
Thank you.
So we say thank you again to the speaker. And now we have a coffee break, 30 minutes, and we come back for the last talk.
Todavía no alcanzo a ver qué pasó.
Oye, eso nunca lo había visto, porque todos vimos la mariposa, regresaste y cuando otra vez te fuiste a esa diapositiva ya no estaba, nunca vi algo así.
Nunca me había pasado esto, Jorge, jamás. Y si no me hubiera pasado esto, capaz no me creerías lo que pasó antes.
probar a piece of. Toma.
¿Listo? Okay, so we will continue now with the final session of the day and of the workshop. Yes. And so for the last talk, we have Dr. Jorge Amin Seman.
Yeah, that's correct.
So, well, Jorge studied physics at the university at UNAM. Then he did his PhD in Brazil, and he did a postdoc in Florence, in Lens. So, well, I think it's time. I'll let you give the talk. The last is saved for last. The best is saved for last.
Oh, no. Okay. Thank you very much, Asaf. So, I want to thank the organizers for inviting. Yeah, I know it's strange that the organizer also speaks, but I thought that it was, since giving the context, it was a nice opportunity to talk a little bit about the work that we are developing at the Ultra Cold Matter Laboratory here at UNAM. So first of all, I want to thank all the previous speakers because all of them have explained many of the concepts that I will use in this talk. And the main idea is to show you what we are doing, what we have done in the last years. This is a new lab that has been constructed in this institute during the last 5 years. And finally, we are starting to get our new results, our first results. So this is what I'm going to talk today. Okay. So basically, the outline of the talk is very simple. I will give you a brief introduction, which is within the context of the workshop. Then I will present our machine, our experiment. So I will I will provide a little bit more of details on how ultra cold gases are produced, and then I will show you some preliminary results on the studies that we are performing now. Okay, so let's start with the introduction. But basically, in the introduction, I want to punctualize, let's say, the main concept behind all the talks. That is the idea of macroscopic quantum system. But basically, quantum gases are atomic many-body systems whose macroscopic behavior is determined by quantum mechanics and quantum statistics. In particular, they are systems that can be described by a single wave function, which corresponds to the single quantum state that is occupied macroscopically by all the atoms. And basically, the main idea is the superposition of waves, which happen at very low temperatures. And of course, one of the most emblematic examples is Bose-Einstein condensation, in which we have a big number of particles occupying a single quantum state. And in this way, we can define easily a macroscopic wave function that describes the whole many-body system. And of course, this high degree of coherence in the system has very interesting consequences. And one of them, as has been shown in this workshop, is the phenomenon of superfluidity. And one of the consequences of superfluidity is the possibility of forming quantized vortices. So what I'm showing here are two pictures of a Bose-Einstein condensate with these darker regions here which correspond to vortices. And these are all vortices having the same topological charge, and they arrange exactly as Karen showed previously in a lattice. So, but to have superfluidity, as also has been explained before, not only macroscopic occupation is needed, we require interactions. Okay, so oh wow, this was not me. Okay, so Victor made a super nice talk explaining how two fermions interact. So I just have a little reminder here, but the main idea is that when one considers two interacting particles at very low temperature, you cannot see them anymore as particles, and you see them as two waves. You can see them as two waves, which have a two-body wave function that describes the collision. Okay, and when one goes to very low temperature, is that the collision can be parameterized by a single constant, which is this scattering length, and the cross section is this constant here. So for this reason, you can find in the literature that cold particles interact as hard spheres whose radius is this scattering length. But I think this is a very bad way of seeing it. I prefer to think of having the two atoms, and they start to feel each other, or they start to influence each other when they are a certain distance apart, which corresponds to 2 times the scattering length. And of course, when we work with identical particles, we need to consider symmetrization or anti-symmetrization, depending of if we have vortices or bosons or fermions. And in the case of identical bosons, what we find when we symmetrize the wave function of this pair of colliding particles is that the collision cross-section is still finite. But for identical fermions, it goes to 0. So two identical fermions do not interact because of the Pauli exclusion principle. They statistically repel each other. They don't see each other. So of course, this has very important consequences. So in the case of, I'm sorry. So in the case of a gas made of identical fermions, the ground state of this many-body system is something that looks like this. No? So here I have a box with quantized levels. And what we have here is that the fermions, since they repel each other, we cannot put all of them in the same level because of Pauli exclusion principle. And what we have is this way of occupation of the different states, which is known as Fermi C. Okay? So there is no macroscopic occupation of a single state. And of course, there is no superfluidity. Okay, so the system is not as interesting as the systems that has been shown during the workshop. But of course, we can make the system more interesting if we introduce somehow interactions. And the easiest ways to introduce interactions is simply by not using identical fermions. So if two identical fermions do not interact, they have 0 scattering length, we simply create a Fermi mixture, and then we will be able to define a scattering length between two different fermions. And then the ground state, instead of one boring Fermi C, now we have 2 boring Fermi Cs, okay? But that they interact between each other. But of course, the scattering length is the parameter that describes how collisions occur. And of course, to form a pair, like those that have been explained before, the atoms need to collide. So depending on how they collide, we can form different types of pairs. So what happens if, for instance, a very easy to imagine pair is a molecule. We have two different fermions, and they form a molecule. Now we have one single particle whose total spin and total internal angular momentum will be the sum of both of them. And this has to be an integer number. So this composite particle will behave as a boson, and then condensation of identical molecules is possible. So you see, if we introduce interaction, no matter how small it is, if it is positive, it turns out that a molecule is possible, and then we can transform our Fermi sea into a Bose-Einstein condensate, in which, again, superfluidity is possible. But of course, it's not the only type of pairs that I can form with two different fermions. Cooper pairs, or the equivalent of the Cooper pairs from the superconductivity theory, are also possible. Okay, these are possible whenever the scattering length turns out to be negative or the interaction is effectively attractive. And this is simply a pictorial representation. Of course, Victor put this very clear. It's not easy to draw how the Cooper pairs are. So typically people imagine them as pairs that are formed in the Fermi surface, which means these are pairs that are formed in the top of the Fermi sea. And again, we can define a macroscopic wave function that describes the whole system. And then, as has been already explained, this quantity, the scattering length, can be externally controlled through these Feshbach resonances. So the scattering length you can change the value of the scattering length by applying an external magnetic field. I'm not going deep into the details here, but here I'm showing you what in practice happens. So this is a real Feshbach magnetic Feshbach resonance. So what I am plotting here is the scattering length as a function of the magnetic field. And what it is very important to realize is that there is a value of the magnetic field in which this parameter diverges. And then if I go to the right, I have that the scattering length is positive. So the Bose-Einstein condensate state is possible. There is a region in which this is negative, so the BCS superfluid state is possible. And then we have the unitary limit, or the BEC-BCS crossover that has been already discussed as a regime which is quite in the middle. It's neither a Bose-Einstein condensate, neither a BCS superfluid, but in any case, the important quantities is the formation of the pairs, okay? And another important quality is that this system is also superfluid, okay? And then the demonstration of the superfluid nature of these three regimes has been achieved experimentally in this very emblematic paper from 2005 from the group of Wolfgang Ketterle, in which he shows the presence of vortices in all the across the BEC-BCS crossover. So we experimentally know that these systems are superfluid. Okay, the way that these people create the vortices in both works either with pure bosons or with composite fermions is somehow transferring angular momentum into the system. So what you see here is a Bose-Einstein condensate or a Fermi superfluid, which is trapped in a sort of optical tweezer, which is this red region here. There are two coils, which are these blue loops that we use or that are used to apply the magnetic field for the Feshbach resonance, and then there is a set of laser beams that rotate and they transfer angular momentum into the sample, and the vortices are formed. Of course, this is not the only way to produce vortices, but it's a very easy to understand one. Okay. So, of course, one of the questions that we have done since the creation of the laboratory is related to this. Is it possible to have turbulence in a superfluid? And the answer is yes. And one of the main ingredients are these quantized vortices. So, of course, this is not a new question. It's not something that crossed across our mind just now. The idea, it's a little bit old, from the 50s. Richard Feynman was the first one in wondering if turbulence was possible in superfluids, and he used to imagine this as a tangle of quantized vortices. Okay? And 2 years later, Joe Bienen observed, he's from, I think, Newcastle University in England. He observed turbulence in superfluids for the first time in the only available superfluid that there was at that time, which is superfluid liquid helium. Okay? Now, there is an important limitation that makes this old problem is interesting even today, which is the fact that liquid helium is a very complicated superfluid, in fact, because it's very dense. And as Giacomo explained, the condensed fraction and the superfluid fractions are very different. So while the system is superfluid, it's completely superfluid, the condensed fraction is very small, and then interactions in this system, since the system is very dense, you cannot describe them anymore with this simple hard sphere model. Okay? And one of the consequences is that due to this high density, the size of the diameter of the vortex is very, very small. So this quantity here is known as healing length. Also, depending on the context, you can call it correlation length. And as you can see, it is inversely proportional to the density of the system. So in the case of liquid helium, the diameter of a vortex is 0.1 nanometers. So it's like few atoms of diameter. They are very, very small, so they are very difficult to observe. On the other hand, for a dilute gas, like the gases that we study in our laboratory, the density is several orders of magnitude smaller. So in this case, the healing length, or the diameter of the vortex, is 1 micron, which is it's huge compared with this other quantity here. So for this reason, studying vortices or turbulence or these excitations in dilute quantum gases is a very good idea, because you can directly observe them by optical means. So in this sense, maybe this is not really the first study done with quantum gases, but I think that a very important result in this kind is the work of Makoto Tsubota, in which he shows that he considers a dilute Bose-Einstein condensate, and theoretically he puts turbulence on it, and then calculates how the energy is distributed among the fluid. And I'm not explaining into detail, but he found that the kinetic energy distributed along the scale lengths, the different lengths of the system follows a power law. And what is very impressive is that this power law is exactly the same that you would have in a classical turbulent fluid. So this is very interesting, because this means that this behavior is way more universal than we thought before. And also superfluids behave, the turbulence behavior in a superfluid, in a quantum fluid, shares a lot of similarities with a classical one. And finally, the pioneer work on quantum turbulence in Bose-Einstein condensate comes from the group of Vanderlei Bagnato in the University of São Paulo, where he observed turbulence in a Bose-Einstein condensate for the first time 10 years ago. So what would be the contributions that our laboratory can do to this problem? Well, we are proposing to study in a very completely different superfluid, in the sense that we have 3 very interesting areas: quantum turbulence in one side, fermionic superfluidity in another side, and strong correlations or strong interactions in the other side. And we put them all together, and we find a very nice region in which there is no research at all for the moment. So this is where we want to work. So we believe that this is an interesting scenario to study this old phenomenon. In particular, we have a knob, we have a parameter that we can control that has not been controlled in any other previous experiment, which is the scattering length. And one of the questions that we would like to answer is if the energy distributes exactly following this power law that I showed before. Okay, so now let me present you what we are doing in the lab and how we generate fermionic superfluids. So basically what we have done is we have selected a specific fermion, which is the isotopes of lithium-6. And of course we need two different fermions. So the way that we do these two different fermions is by selecting two different spin states of the same hyperfine level. So we have two different fermions. And we chose this atom because it has a very nice Feshbach resonance. It's very broad. It's almost 300 Gauss in broad. So this means that we can control very precisely the scattering length. And this is just a picture of how lithium looks like at room temperature. So of course, to produce these kind of systems, we need to isolate them well. We have this. This is a cartoon of our. It's not a cartoon. It's the actual design of our ultra high vacuum system. So basically, there are two parts that are very important, which are the ones that I want to talk. We have an oven in which we put the lithium inside, and then we heat this to produce a very dilute gas that travels through all these tubes up to this chamber in which we cool down and produce the superfluid or the sample. I don't want to enter into details of the other parts. And something which is nice about our experiment is that we have a very nice optical access. So this is a cut of our chamber, and just to show how many viewports we have to observe and manipulate the sample. And here I'm just only placing the magnetic coils that we are going to use. In particular, the Feshbach coils will be on top, top and below the chamber. Then I don't want to go deep into details on this part, but we use very standard laser cooling techniques to cool down this vapor coming from the oven. So what I'm showing here is the energy levels of this atom of lithium-6, and what you can see is that we have the ground state, and then we have the first two excited states, and the transitions between these two first excited states are known as D1 and D2 transitions. So to produce our first cold sample, we use these cycling transitions from the D2 line. So what I'm showing here is how these fine states split into these hyperfine states. And what you can see here is how the configuration of lasers and magnetic fields are done. So this is a top view of our chamber. And then what you see are the laser beams at these frequencies and a magnetic field. And in this way, we can produce what is known as magneto-optical trap. So what you are seeing here is a picture of the inside of our chamber. And this blue, very bright ball is a sample of atoms containing a lot of atoms, 10 to the 9 atoms of that order, at a very high, sorry?
You said blue.
I said blue. I meant red. I'm moving too fast, sorry. So the temperature of this sample is of the order of 7 millikelvin, okay? Superfluidity in these kind of systems occur at way lower temperatures of the order of nanokelvin. So even if this is the coldest object, liquid nitrogen, that is probably the coldest object that you have seen or you have played with, is like it's 70 Kelvin. Okay, so it's way hotter than this. So even if this is a very low temperature, it's still very hot for our goals. So what we do is to cool down even further the sample using now the transitions from the D1 line. So I'm again not giving a lot of details on how we do that, but the mechanisms are all related to light and matter interaction. This part is done in absence of magnetic field. And basically the result is that we are able to produce a sample of, we can take this red spot and cool it down even more. So we lose some atoms in this process, but we end up with a temperature which is 4 orders of magnitude lower, from 7 millikelvin to 45 microkelvin. So it's a huge improvement, but again, I want to be 1,000 times lower in temperature to reach superfluidity, so this is not enough. So what we are going to do is to transfer the atom into a conservative trap. So what we do is that we focus a different laser with a frequency which is very far detuned from the transitions that I showed before. Okay, and this creates a harmonical trap, a harmonic potential, and what I'm showing here is a picture of the atoms from the magneto-optical trap, which is this big ball, with the laser trap, with this laser beam focused on the middle, so you can see how some of the atoms are transferred into this elongated trap. And then we switch off this magneto-optical trap, and we simply keep the atoms in this optical trap, which is it's a very weird geometry, but it still is a three-dimensional thermodynamic system. Now I just want to give you some few words on how we produce these pictures. Basically, we use a technique known as absorption imaging. And the idea is that we have the atoms here, and we shine the atoms with a resonant laser beam. And this produces a shadow because all of the atoms will absorb the light. So they will produce a hole in the beam. And then what we do is to produce an image of this shadow. And the way we do it is that we take advantage of the very nice optical access that we have in our chamber to put a very primitive objective microscope composed by just one aspherical lens, which is very close to the atoms. So in this way, we can produce very nice images. Our imaging system, this is a better version of what we had before, so it's still under characterization, but with this imaging system, our resolution is a little bit better than 2 microns, but of course, in the future we can improve it. So this is it. We have our sample trapped in this magneto-optical, in this trap, and this is the moment in which we apply the Feshbach magnetic field. Okay, and we use initially this Feshbach magnetic field for doing 2 things. Okay, first we set the magnetic field right around the crossover, in which the scattering length is huge, and this allows us to maximize the collisions between the atoms, and in this way the atoms rethermalize faster. So we can cool down very fast, very quickly. But also, as I told you, in order to have superfluidity, we need to create a spin mixture. So the magnetic field will help us to split the levels of the ground state and to create the two, to be possible to have 2 separate spin components. Okay? And then we apply a third process of cooling, which is known as evaporative cooling, in which we have our harmonic trap with a distribution of energies of the atoms. Since this is not a Bose-Einstein condensate or a superfluid jet, this will be a Maxwell-Boltzmann distribution that will describe the system. And then we will find a way, which is simply reducing the depth of the trap for the hottest atoms, or the more energetic atoms, to escape. So we create this out of equilibrium Maxwell-Boltzmann distribution. But of course, the system very fastly rethermalizes into a new equilibrium distribution, which a lower temperature. And this is why we choose to have the strongest interaction possible, because in this way, this process happens the fastest possible. Okay, so this is how we cool down. So what I'm showing here is the power of the laser beam of the trap as a function of the time. And then I'm showing here a very important quantity, which is the phase space density. And basically, when the phase space density is larger than of the order or larger than 1, the quantum coherence happens, and then superfluidity and all these phenomena are possible. So basically, at the end of the evaporation, in which we keep only the coldest atoms, the quantum degenerate regime is possible. And finally, we can have fun with the different regimes that we can produce. So for instance, if we choose to have to set our magnetic field in the region of the BEC, then we can produce a very nice Bose-Einstein condensate. So what I'm showing here are three pictures of the sample at 3 different temperatures. So above the critical temperature, the cloud is a Gaussian gas, which is classical. And then right at the critical temperature and a little below, we see how the Bose-Einstein condensate appears, how the ground state is macroscopically occupied. And then and this is characterized by this bimodal distribution, in which we have still a non-condensed phase in contact with this condensed, more sharper distribution. And then as we decrease the temperature and we go well below critical temperature, we have a nearly pure Bose-Einstein condensate. So we are very proud to say that this is the first BEC in Mexico. We achieved it on 1 year ago, 1 year and 1 month ago, at this time. So for the students, it's very important to understand that the nice things in the lab, at what time they occur, okay? And right now, we are able to produce samples containing a little bit more than 4,000 molecules, and at temperatures which are lower than 20 nanokelvin. And something that is nice about the experiment is that we are able to produce a new superfluid every 14 seconds, okay? But of course, we chose fermions because, in my opinion, they are more fun, because we have more regimes to play, okay? We have the whole BEC-BCS crossover. So what I'm showing you here is 3 pictures of the sample at 3 different interacting regimes, but at the same temperature. So you can see how the density of the cloud changes really a lot. So you can see how let's say, the nature of this, although these 3 systems are superfluid, the density are very different. So this is something that we are very proud to say. This would be the first ultra-cold fermionic system in Latin America. So Patricia Castillo is here. She knows in Brazil, they have done the first Bose-Einstein condensate in Latin America in 2007. But up to now, they have been working only with bosons. And now I would like to show you very, very, very preliminary results of what we have been doing during the last couple of months in the lab. So basically, we decided to work only in the easiest, or not the easiest, but the better understood regime, which is not so strongly interacting Bose-Einstein condensate. We chose this because we understand well the theory is, across all the crossover, the theory to describe the system is the simplest, so we can understand better what's going on. Okay. And basically the idea is that we have this elongated dipole trap, which is a combination of the trap of the field of this optical dipole trap, but also there is a small curvature. I forgot to mention this before, but the Feshbach field also has a small curvature that allows us to confine in the longest direction a little bit. Otherwise, the cloud is super long and it's difficult to analyze. And basically, we have this harmonic potential. And at the end of the evaporation, the superfluid that we produce has these characteristics. It's a cylindrical, it has cylindrical symmetry, which means that the X and Y frequencies are exactly the same, which is in this case 163 hertz, and then the actual frequency it's 11 hertz. So what we have is this cigar-shaped superfluid, and the harmonic potential looks more or less like this. Okay, so we have a radial term and an axial term. Okay, and what is important to understand is that the radial confinement is provided by the optical forces of the dipole trap, while the axial confinement is provided by the curvature of this magnetic field. And this is very nice because this means that we can change independently these two frequencies. So we can modify independently, let's say, the length and the diameter of the cloud. Okay? So one question was, before starting to do all these vortices which are somehow complicated, can we produce any other type of collective excitation just by modulating the trap? So what we did is that since the frequency, the radial frequency depends exclusively on the power of the optical dipole trap, we simply modulated sinusoidally, the power using more or less in this way. Okay, so this means that we are relaxing and tightening. Okay, the cloud. Okay, and what we observe is something that is actually very well known, is something known as breathing mode. So what we are plotting here is the orange curve. Okay, the orange curve is the power. It's simply this. Okay, it's simply how we are changing the power of the trap. And then the blue curve is the diameter of the cloud along the radial direction. And as you can see, we produce a sort of excitation which is a maximum at a certain time. So basically what it is happening is that because of this excitation, the cloud is shrinking and expanding as a function of time. So this is why it's called a breathing mode, because when you breathe, your chest expands and contracts. Exactly the same as the cloud. Okay? And then the the frequency of this breathing mode happens to be twice the radial frequency of the trap. So this means that this is a sort of parametric phenomenon. Okay? But then something else happened. So we are exciting along the radial direction, and at a certain point we see a density modulation, a periodic density modulation along the axial direction. So we observed this, and this is what we have, searching in the literature, we identified this as Faraday waves. So what are Faraday waves? Faraday waves were discovered by Faraday in the 19th century, and basically in one of his experiments he took a fluid, okay, in for example, a Petri dish, a not very tall glass, and then he perturbed in the system in one direction, and he observed the formation of patterns along the perpendicular direction. Okay, and then there is a connection between the frequency, the pumping frequency, and the frequency of the pattern, which is a factor of 2. Okay, so we observe exactly the same. We excite along the radial direction, and we observe a excitation propagating along the orthogonal direction. Okay. So these are very well-known type of excitations that happen in many nonlinear liquids. So where is the nonlinearity here? Well, this is the Gross-Pitaevsky equation that has been very well explained. And I kept, I'm sorry, there is a mistake in this equation. This minus sign shouldn't be there. Yeah, there was a student who got, I got very mad because he made this mistake. So it's embarrassing. I'm sorry. And the nonlinear term is the interaction term here, which depends on the square of the wave function, which is exactly the same equation that Karen showed in the paraxial approximation. So probably there is also an equivalent of Faraday waves for light. But of course we are not modulating this. So why the Faraday waves are appearing? The reason is that since we are modulating the trap, we are also modulating the volume, which in consequence modulates the density, which in consequence modulates this term, which in consequence I can see it effectively as a modulation in the scattering length, which is the term that parameterizes the nonlinearity or the intensity of the nonlinearity. Okay? So to try to understand a little bit better what we were observing, and again I repeat, these are very preliminary results. We are still working on this. We decided to follow one of them. There are a lot of theoretical work around, but in my opinion, one of the easiest to follow is this proposal from this author, which is basically proposing these ansatz. So we have this, which makes a lot of sense. It's the wave function is something that has a periodic modulation on it, and this modulation depends on time. It's a dynamical phenomenon. Okay, and then we substitute this proposal into the here it's well written into the Gross-Pitaevsky equation. Okay, and then if you linearized this nonlinear equation, what it happens is that you find that when you substitute these ansatz, you obtain this new equation here, okay, which this function that you have to obtain is related to the amplitude of this spatial modulation in this way as the real part, okay, because of course this is a complex function, okay. And then we have this parameter here, which depends on the wave vector of this wave here. Okay? And something that is very nice is that this equation is exactly the Mathieu equation, which is a dynamical equation which appears in many other dynamical systems. And in particular, something that is very nice is that if you analyze this equation as a function of the amplitude of this modulation and the wave number, you find this sort of phase diagram in which there are these regions, these gray regions of stability, which means that in these regions, this solution is true. Okay? And then if you, I'm not explaining this, sorry for showing this, but if you introduce some dissipation into the problem, the stability regions change like this, but it's exactly the same. It's more or less the same. It's the same idea. And so what we did to analyze our data is exactly to fit a function, the density. So what you are seeing here, the blue curve, is simply the integrated density along the x direction, along this vertical direction here. And then we fit this this oscillatory function, okay? And again, what we see is that the amplitude of the modulation, okay, also depends parametrically somehow on the excitation, okay? Which again, the orange curve is not a fit to this data before you start bothering me, Jackson, okay? This orange curve is simply to show how the excitation is done, okay? But of course, when you want to analyze this type of function, taking the Fourier transform helps. So what you are seeing here is a picture of our Faraday pattern, and then below what you see is the Fourier transform of this photography. So of course, this is in the space, the normal space, in the normal space. Sorry. Here we have that this is in the reciprocal space. So what this gives us of information is that the central spot corresponds to the whole condensate, and then these two spots are corresponds to the wave vector of the Faraday wave. Okay, so this is a video that the students prepare, in which you can see how the condensate and how the density of the condensate evolves during the excitation, and at some point you see how the Faraday pattern appears. So it's very nice, I think. And then we prepare exactly the same video, but for the Fourier transforms of the pictures of the video before. And again, you will see at some point this the wave appears, because we will see some structure. At some point it will be very clear over here. Okay, it's right there. So through the Fourier transform, we have access to the two quantities that are important, which are the amplitude of this modulation and also the wave vector value. Okay, and we observe something like this. So this graph is not, I know it's not beautiful yet, because these are this comes from a first set of data. We are still learning how to analyze these phenomena. But basically this black, so what you are seeing here is the amplitude of the excitation and the wave vector of the Faraday wave. Okay, so this first region, this black region, is like the condensate itself. And then what I want you to notice is that there appears some structure, which somehow resembles the stability map of the Mathieu equation. Okay, so this is the most important result that we have up to now in the analysis of this phenomenon. Okay, of course, the goal is to observe and characterize this excitation. As I showed before, Faraday waves have been studied in Bose-Einstein condensates, but nobody have observed them across the BEC-BCS crossover in more, let's say, sophisticated superfluids. So of course, the goal is to characterize this excitation across the BEC-BCS crossover. Theoretical description is fundamental to properly analyze our data, so we have established collaborations. So in the BEC side, we have this team, Victor Romero, Rosario Paredes, and Alexis Dominguez, their student, that are starting to do the simulation of this system. And also in the BCS side, we have Santiago Caballero and his student Miguel Torres, also modeling at this interacting regime. But wait, I started saying, oh, we want to do quantum turbulence, and then it looks like we deviate a little bit. Actually, not. There is a very recent work. So what this shows is that the Faraday wave problem is reviving, in which they study, again, this type of parametric excitations in elongated Bose-Einstein condensate. And as they increase the excitation, the amplitude of the excitation, they observe this Faraday wave pattern, but also something else. So in this article, from the group of Randall Hewlett, but also Vanderlei Bagnato is collaborating here, initially they observe this very nice, very periodic Faraday pattern. But as they keep the excitation on, or as they increase the amplitude, the system breaks down, okay, into something which is not periodic anymore. So this is what they call the granulated state. So there are many questions concerning if these individual lobes are superfluid or not. But they mention in the conclusions of this article something very interesting, which is that the multi-characteristic nature of quantum grains is supported by our observation of additional anomalous features in real and momentum space. Indeed, we find signatures of different coexisting phases of perturbed quantum systems, such as quantum turbulence and localization in granulated states. So maybe this is a different route to attack the problem of turbulence. It's somehow connected what we want to observe, but of course in a first stage of our work we want to simply characterize the Faraday wave problem, which is already complicated enough, and for sure our first approach to turbulence will be to generate vortices in a much more direct way. But anyway, I think this is an interesting connection. And finally, let me introduce you the team that has all the results that I have shown is the result of a team work. So, so let me show you in order of appearance in the lab. So we have two master students, Diego Hernandez and Eduardo Padilla, and we have 4 undergraduate students, Andrés Gutierrez, Sebastián Morales, Melanie Bautista, Karen Cuervo. There is a 5th undergraduate student, Javier Cárcamo, but he was not in the lab the day we took the picture, I'm sorry. And of course, it's very important for me to mention Dr. Jackson Poveda. He's a researcher of our group, and he collaborates in our laboratory and have been doing a very important job. Of course, this is part of a larger effort to create this laboratory. So I want to do a special mention to Rocio, which is the leader of the National Laboratory of Quantum Matter, and our colleagues in this adventure of creating this laboratory, Victor and Rosario, and Santiago that recently joined in these Faraday wave studies. And also it's important to mention Carlos Gardea, our técnico académico, which is helping us a lot in the developing of electronics and instrumentation. And of course, for me, it's important to mention Giacomo Roati, also a very important collaborator in the construction of the experiment. And finally, I want to thank you, and I will be happy to listen to questions. So how is my time?
Just in time. Okay, so are there any questions? Victor?
Not a question, but I'd like to make 2 comments.
Okay.
One is the importance, just for the rest of the people here, the importance that you have an elongated BEC to see the Faraday waves. And I'd like to connect it with Patricia's talk, Giacomo and Rosario, that when you have a 3-dimensional BEC, and then you make a quasi-2 or quasi-1-dimensional, the frequency, the scattering length in the resulting
System.
Fluid, the scattering length is divided by the frequency of the ones that you took away.
Okay.
So in the 1D, you are sort of ignoring the omega R, the omega transversal. And so the effective scattering length of the 1-dimensional, quasi-1-dimensional, it's not 1-dimensional, it is the scattering length of 3D divided by the frequency. And that's why when you do this in the experiment, then the effective scattering length of the 1-dimensional is doing that.
Okay.
That's the connection.
So it's more direct than this
Yes, of course, it is a
100
it
steps
is,
connection that I did.
You can do it by hand and show that comes naturally.
Okay, thank you.
And the other is a confusion that I also had, that Diego pointed out, is that the tongues are unstable, not stable. If they were stable, you wouldn't see them. If they are unstable, and that's why they grow.
Okay.
So actually, if you
exactly.
keep bothering the system, it blows up.
Yeah, you mean
Right?
you are out of equilibrium.
Exactly. So the tongues are the unstable state. I also thought were the stable, and Diego corrected and said, no, they are unstable. So it's good to
Okay.
to keep that. Just a minor.
Thank you, Victor.
Minor.
Yeah, I mean, what I meant is that these are the regions in which the pattern can
Exactly.
be observed.
That's what they are
Sorry,
observed.
The,
That's for
the
sure.
word is wrong.
Yes, yes.
Thank you, Victor.
They appear there, of course.
Yes.
Yes.
There's a question over there.
Yes, I have a couple of very simple questions, I think. But you had one slide about the breathing of the thing.
Yes.
And I don't know if I understood correctly, but it was against time and it looked like it increased, like it breathed more and more, and then it decreased, right?
Yes.
And I was surprised by that because I thought it would be like a harmonic oscillator. Like if you continued pumping it, it would continue oscillating. No? Like why?
You mean this one, right?
Yes. Well, you had others, but yeah, that one too.
No, this is actually, the one that you meant is this one.
Yes, indeed. So it surprises me that it has, like, looks like resonance or something, and then
Yes.
it decreases. And I was wondering why, and also if there would be like a resonance frequency at which it would like breathe more.
So this is an effect of the fact that since this is a parametric excitation, the cloud starts to heat up, and we start to destroy the condensed state. So we are exciting during a too long time. So actually the interesting region would be like this central region, and this is where we are going to perform. At this time of excitation, we are going to perform the experiments. Okay?
Yes. And just a slight technical question, is the laser with which you make the elongated trap, is it detuned so that it doesn't push it away, so that there's no scattering force?
Exactly.
Oh, okay, yes.
Yeah,
Thank you.
I mean, it's very away, it's several nanometers, it's hundreds of nanometers away to any transition. Okay?
Thanks.
More questions? Yes.
Okay,
Georgie.
Patti, don't be bad.
Thank you for this very nice talk. So my question is, so the patterns you see, you said they are dynamic in time,
Yes.
but do you mean it's the time that you produce the excitations or the time that you wait in trap? Do you do a waiting time or?
Okay, in this case, in both cases is dynamical. So if you excite and then leave, you still have this breathing mode, and you still have the appearance of the Faraday pattern, and then the Faraday pattern still moves. But also you have some dynamics when you keep pumping. So what we have shown up to now is in all the pictures that in all these videos, the excitation is always on. We are still moving. So this is connected to the previous question. This is exactly why we lose all the atoms at the end, because since we keep the pumping on, the system starts to heat up. Okay, yeah, Giacomo. Or you have another? No? Okay.
So maybe this is nasty.
Oh my God. Please no.
So actually, one is of course for sake of, of clarity. What do you expect if you move to the crossover? And the second is maybe we discussed also already. I mean, Faraday was living hundreds of years ago, and observed this Faraday wave in a classical fluid.
Yes.
So what is different, and which is the connection between Faraday wave in classical fluids and in a quantum superfluid?
Okay, so the short answer is that I don't know and I don't know. But we can say, I'm not completely certain, okay? But we can discuss a little bit. So what we expect across the BEC, BCS crossover, there are just one theoretical work from a Chinese group, right? Which actually, it's at least for us experimentalists, was impossible to understand that work. But the Faraday pattern still forms. But what it happens is that the pattern gets closer and closer. So the K becomes larger and larger. So what we expect is something like you have shown in the Joseph sum experiment, that the frequency increases, reaches a maximum, and then decreases. We expect to see something like that. So how this K value is connected to microscopic properties of the system, what can we say about the superfluid, if we can form a Faraday pattern and then analyze it and say, oh, the scattering length is this, or oh, the order parameter, we can measure the order parameter. These are very interesting questions, but we yet don't know. And actually, well, we expect that at some point from our collaboration with the theoreticians and the further studies that we are going to do, something else comes out soon. And then concerning the question of what's the relationship between quantum fluids and what's the connection? Well, the connection that I think is that I think that the connection here is that this makes very clear that our system is a macroscopic wave, and this is and in this way, just like Karen was talking, since these are waves, there has to be a connection with any other kind of waves. So the Faraday wave in a classical fluid does not describe the whole fluid. It only describes the oscillation that you produce on it, which is directly connected with this system because it's also a macroscopic wave function.
Just a comment more.
Yes.
But then is another question.
Okay.
If you take an ideal Fermi gas,
okay.
What do you expect to see?
I won't expect the formation of Faraday waves.
So this means that because also one particle is a wave, so you need interaction anyway between them.
I mean, you need to have a whole. You need a macroscopic wave function. You need a big coherence in this. And then okay.
It must be nonlinear.
Also, there is the ingredient of nonlinearity that you don't have in the ideal Fermi gas. But okay.
The actual Faraday waves, you see, there is a colleague here at the Institute, Rafael Barrio,
Okay.
who many years ago, he had one of these talks for everybody, beautiful one, and he had a petri dish, not that shallow, it was like this.
Okay.
And then he put underneath a speaker.
Okay.
Just make it to vibrate. And the patterns form at the surface. And this is amazing, because you have patterns of all symmetries. Sometimes symmetry 5, which is very strange.
Okay. So you have a pentagon or something.
No, yeah, that's right, like a pentagon, like it opens in 5 areas differently.
Okay.
It is beautiful, just with a speaker and water. And so he used this for a show. And this is, the nonlinearity is crucial, right? These are very shallow waves at the surface. They are surface waves. And so I believe that the nonlinearity is what relates the problem, not that these really are the patterns that Faraday was talking about. I think it's more the name only, I believe. These systems are, this, I think it's in a fluid, it's important to forget that it is viscous. It is non-linear, but without viscosity to explain well the Faraday patterns of Faraday. And here, you also don't have viscosity because it is a superfluid, but you also need the nonlinearity. Probably that's the deeper connection. We should look at that. It's probably the deep connection between the two of them.
Thank you, Victor.
Maybe, well, I have 2 short questions, but so they're actually very short. When you draw in this Bagnato turbulence paper, the drawing on the right is artist's impression, or it comes from?
This.
Sí.
It is 2 of them. So this is what, it's an artistic representation of these clouds. So if you see there is like a sort of vortex.
Yeah. My question is
like
what's the connection?
One,
if
then,
it's,
and then
how
this.
sure? How sure are you? I mean, is it like interpretation or is it like some analysis?
No, it was a pictorial picture just to represent what we think we are observing.
Okay.
Okay. I don't want to say anything else.
Okay. And the other question is about the. So how does the frequency of excitation compared with the radial excitation?
Okay, that's a very important question. So in the BEC side, let me go to a...
Yeah.
So in the BEC side, it is connected in this way. So the frequency of the breathing mode is twice the frequency of the radial frequency. It's twice the radial frequency, okay? But as you move across the BEC-BCS crossover, this dependency changes because actually this factor of 2 is actually an algebraic function of a parameter of an exponent which comes in the density of the wave of the equation of a state of the system. So as you move into the BEC-BCS crossover, this factor of 2 decreases, okay? So if you want to excite a breathing mode, well, you can in principle you can excite the breathing mode. However, if you do like a sharp kick into the system, one of the collective modes that you can excite is the breathing mode, okay? And the frequency will be related to the equation of a state of the gas and the frequency of the radial and of the frequency of the radial confinement of the harmonic trap. But it will go to, so more or less it starts in 2. Then as you move in the crossover, it goes to 1.5 and then it increases again, but it never reaches 2 again.
But so the question here, you excite resonantly the big omega is
Yes,
the breathing mode omega?
Yes,
okay.
We are exciting, or at least in the BEC side. We have done some tests in the crossover, but we still don't are able to form the Faraday pattern.
Okay. So are there more questions? I think we're running late, so I guess you can always ask Jorge later. So I think we should finish, no? Yeah.
Yes.
Okay, so let's thank Jorge.
Thank you.
And thank the organizers.
So, okay, thank you very much, Asaf. And thank you, everyone. I guess we can close our workshop now, but not before saying that it was, for me, a big pleasure to having you, all of you here. I think that it was a very, very nice, something that, I think that one important characteristic of this workshop is that every single talk has been connected to each other. And I don't know how common in workshops this can be, but I think this was a very nice characteristic of this workshop, mainly because the type of systems that we were presenting were really different, from light to matter, from bosons to fermions, from strongly interacting systems to weakly interacting systems. So for this reason, I think that quantum macroscopic phenomena are a very interesting research area, which has a little bit for every taste, for everyone. And in this way, I want to end saying thank you very much, and hope to see you in the second workshop on macroscopic quantum phenomena. Thank you.